Okay, so let's talk about the exercise 5 of the worksheet 3.1. Okay, these are interesting examples because we can see that we can have linearly independent families that have an infinite size, okay, because it's for all n that belong to the set of natural numbers. We want to show that, well, let's take the second example first, maybe it's easier. That's the family that is constituted by all the ENX with n in n is a linearly independent family. So how can we do this? We are going to do it by induction. We don't really have the choice in that case when we've got something like this for all n in the set of natural numbers. So let's go for induction. So we have the base case, the induction step, where we have to study we have to quote first the induction hypothesis, and then the induction step, and so on. Okay, so let's see. Base case would be if I take n is equal to 0. So in that case, I just have, let's call my families f0, for instance. F0 is going to be just e0 times x. That is just the vector, which is the constant one, the function, or maybe I forgot to say about that. The vector space we are working in at the moment is, well, let's take the easiest one, is would be the space of functions. Okay, the vector space, there are real functions from R to R, right? And that was one of the basic examples. That's a vector space because you can do a linear combination of real functions and it's still a real function, right? So that would be the constant function equal to 1, this one. Okay, and of course, as we only have a single vector, a single item, the family is linearly independent. Now let's see about the induction hypothesis. The induction hypothesis would be that the family that is constituted from, well, we get E0, we get EX, we get E2X, and we go up to ENX for some n. The hypothesis is that this family is linearly independent. And what do we want to show? We want to show that the family at rank n plus 1, which is, well, the same one as before, except that we go one step beyond the previous one. So we add that last function. This family is linearly independent. So that's what we want to show, right? So what do we want to show? We want to show that if we take the sum of all elements of this family times some real values, and that this sum is equal to 0, then it means that all the coefficients, all the real coefficients, have to be equal to 0. So we want to show that if I take lambda 0 times 1 plus lambda 1 times e of x plus lambda 2 times e of 2x plus blah blah blah, lambda n e of n x n plus 1 e of n plus 1 times x is equal to 0. I want to show, so that's my hypothesis, my assumption. The question is, does that imply that lambda k is equal to 0 for all k equals to 0 up to n plus 1? Okay, so the question is, do we have this implication? That's what we have to show in order to get the induction correctly done. So how do we proceed? This equality is assumed to be satisfied. It's equal to 0, and it's assumed to be true for all x that belong to R, right? Because we are in our vector space of functions, all right? And my items, my vectors, are these functions. Yeah, all right? And so the 0 that I've got here is actually the 0 function. the zero of my vector space here. So that means that the function, the zero function, is the function that for all x in R associates the value 0. Okay, that's my zero function. That's the zero we mean every time we're talking about linear independence. All right. So this equality is supposed to be true for all x in R because that's equal to the zero function of R. Right. So in particular, I can consider the limit. And we're going to take some limit that is going to help us. So let's take the limit as x tends to negative infinity. Why do I do that? Because on the right-hand side of this equality, the 0 is not going to change anyway, but on the left-hand side, when I'm looking at the limit as x tends to negative infinity, all the exponentials are going to cancel. Okay, so I'm looking at the limit as x tends to negative infinity of lambda 0 plus lambda 1 e of x plus lambda n plus 1 e n plus 1 x. And I know that on the other side, I know that this limit is 0. Okay, because the limit of the 0 function when x tends to infinity is just 0 because that's the constant 0. Okay, so let's see, this limit then is equal to all these exponential go to 0, that goes to 0, and so on. All that goes to 0. And what's left then is only lambda 0. And so I get a first information that lambda 0 is equal to 0. So let's sum up. If this is true, then first thing, it means that lambda 0 is equal to 0. I still have to show that all the other lambdas are equal to 0. But let's see what we can do. So lambda 0 is equal to 0. That means that now we know that we have, well, what's left in my equality here is that lambda 1 e of x plus lambda 2 e of 2x plus lambda n plus 1 e of n plus 1 x is equal to 0. Okay, I just got rid of the first one, of the lambda 0 here. Right, so this is what we have. What we can do is we can factor with e of x. We get e of x times lambda 1 plus lambda 2 e of x plus lambda 3 e of 2x. You see, because e of x times e of x is equal to e of 2x, e of x times e of 2x is equal to e of 3x, etc. Plus lambda n plus 1 e of nx. And that is equal to 0. And this is where we can use the induction hypothesis, which is that this family here is linearly independent. Okay? This family being linearly independent, it means that if I'm doing the sum from 0 to n of coefficients times e of kx equals to 0, it implies that those coefficients are all equal to 0. All right? And actually, this is exactly what we have, right? We have that the sum from 0 to n of those coefficients times e of nx, e of kx is equal to 0. The lambda we have in front is just lambda k plus 1 equal to 0. So from the induction hypothesis, that's implying that lambda k plus 1 is equal to 0 for all k equals from 0 to n. Right, meaning that lambda 1, lambda 2 up to lambda for k is equal to n, we get lambda k plus 1, so lambda n plus 1 are equal to 0. Okay, and that's it. We've got, let me get back to black. So fn plus 1 is linearly independent. And then, so we can conclude that this is true for all n, so the family E of nx for n in R in the set of natural numbers is linearly independent. Okay, thank you.